So in this digital control systems technology course, we are going to, the main thing that we'll be focusing on is about digital control systems, but mainly from a technological point of view. That is the main thing to remember here. Typically, digital control systems is a very theoretical subject, and that is how it may be delivered in various places, particularly in engineering courses and so on. But we are mainly focusing it on from a technology point of view. So, briefly, if we, as an overview, what we will be covering in this course would be mainly about software hardware systems, or systems that involve software and hardware systems, and as through the mainly through the practical component, the project component, you will be developing a digital control system. So we'll first briefly go with an introduction to the class, cover some of the briefs about it. Particularly in this course, we will ideally have, once we start the practical sessions, we will have additional instructors assisting with the projects and so on, but it will be announced once we start that phase. And in terms of assessment, again, these percentages may change as we are in a slightly different teaching method for this semester. But anyway, we will a significant portion of your marks will come from the group project that you will be doing. So that is an important part of this course. So you'll have to focus on that as well. And in terms of the main key content that we will be covering in this course, we will go through analog systems and digital systems, a brief about electronics as well, just a refresher, and then talking about hardware software co-design, how we can programming hardware based systems, microcontrollers, that type of a thing. And then we'll talk about control systems, designing control systems, and project will be a key part as well. In terms of main course resources, all the course resources will be shared on LMS as usual, but if you are interested in the previous year's course resources like lecture slides and so on, you can also find them on the common website there, where you can find the digital control systems technology course from previous years. So when we say digital control systems, what we are mainly talking about is it can be anything, any system, as long as it is being controlled by digital signals. So we are using digital signals as a way to control systems, as a way to control how systems are reacting, how systems are performing. So that is sort of the basic idea to look at anything that we can classify as a digital control system. So for example, if you look around in wherever you are now, you may see a number of things that can be classified or categorized as digital control systems. The requirement is the input to those systems are done through some digital manner. So even if you take a simple television with a remote control, normally from a remote control, the signals are transmitted to the television as digital signals, and that is in itself then again making some controls. It is controlling the way that particular system is performing. So that we can take as an example for a simple digital control system. From that we can go to a larger extent to, like, say, a vehicle or an aeroplane. The systems that are there to control those things are also considered digital control system. So from a simple system like a television to a very complex system like an aeroplane, all of them will have some element of digital control. So that is what we are focusing in this module. So before we start discussing about digital control systems, we first need. So when we say systems, we are talking about things that are anything or a set of things that are working together as part of a mechanism. So that is the basic definition of systems. So there are many examples of systems, and we can categorize these systems into two major categories. One are natural systems or naturally occurring systems, and then artificial systems. So, for example, how a human body would function, or how the rivers are flowing, all these things are natural systems, things that are existing in the natural world. Then there are artificial systems or man made systems, things like an automobile and a vehicle, a television, a watch, all these systems, we can categorize them as artificial systems. So that is again a main categorization. So when we talk about systems, it covers a wide array of things. And in this context, we are mainly going to be focusing on artificial systems, particularly digital systems. Then we can also categorize certain systems as what we call as dynamic systems. So with dynamic systems, the main differentiation here is they will change their behavior as time goes along. They will change their behavior depending on the circumstances. For example, we can understand it with a simple example of a fan. So if you have a ceiling fan or a table fan, normally when you switch on the fan will rotate at a particular speed, and that is what it will always do. You switch on the fan today, it will rotate at a particular speed. If you do it tomorrow, again it will rotate at the same speed. But if you think about something like an air conditioner, there the air conditioner would function significantly differently. So you may set a target temperature for the air conditioner. You may say the temperature should be 26 degrees Celsius inside this room. Then the air conditioner would work accordingly to bring down the temperature in the room to that particular temperature. If it is very hot outside, it will cool down it to 26 degrees. If it is cold outside, it may heat it and bring it back to 26 degrees. So with an air conditioner, the way that it is going to perform depends on the environment, depends on the situation. That's why we will categorize that as a dynamic system. Whereas a fan will not do that. It will always perform the same thing. So it will not change its output depending on the circumstances. Then when we talk about control or controlling systems, what we do here is changing the behavior of a system. So again, if we take the example of a fan, many fans also we can control to some extent using the adjuster knob. So we can set the speed of the fan by turning the knob accordingly. So that is a way we control that particular system. In the case of an air conditioner, again, we may have a remote control where we can set the temperature, speed and all. Again, we can control that. But when we think about digital control, the main difference is the control laws or the way the control is happening will be implemented in a digital device. Say, for example, in the case of a fan, normally when you turn the knob, it is an electrical or electromechanical function that is changing the speed. There are no electronics components or digital components. It is just changing the position to a different place, and the motor is getting different amount of current, or it is getting different way of instruction, and it is performing differently. Whereas in the air conditioner, the way it is performing will be controlled by a digital device, like it may have a microcontroller inside the air conditioner, and it may perform accordingly. So that is the main difference between digital control, where the control laws or what needs to happen in the system will be implemented in a digital device. So when we think about again digitally controlled systems, again you may have come across a number of these things in your day-to-day life. Say for example, in offices and houses, it is very commonplace to find uh, temperature control systems, or air conditioners, or heaters, that type of systems, where they are again controlling the performance with, or the temperature within the environment using some digital means. You are giving some instructions to those systems, and then they are maintaining the temperature throughout that space. For example, if we take automobiles or vehicles, for example, again you may find a number of digitally controlled systems, like speed regulators in cars, um, um, braking systems in vehicles, in cars, sometimes even in motorbikes, fuel injection systems in vehicles, again electronic fuel injection, and so on. So these are all digitally controlled systems. So the basic control logic will be implemented in digital devices, and then they are controlling some other system. Then even things like, even much more complex things like, say, aeroplanes, or autopilot systems in aeroplanes, automatic landing taking off systems, automatic navigation systems. So all these things are also, we can categorize under digitally controlled systems. And another sort of another sector within digital control systems is robotics. So one of the foundations of robotics is how things can be controlled digitally, and again there we will use digitally controlled systems. So these can be, say, robots that are used in manufacturing plants, for example, uh, welding robots, and so on. So these are all again can be controlled digitally. So in that case, they will be again categorized as digitally controlled systems. So when we talk about digital systems, there are a number of reasons why we are using a lot of digital systems these days. Particularly comparing them to analog systems, there are many advantages that we can get by using digital systems. So, for example, speed is an important factor for using digital systems in many situations, particularly when we are using fairly capable computing powers, fairly capable computing systems. Then they can do much higher level of computations at much higher speeds. Similarly, the same systems can also produce outputs in a much more accurate manner. Say for example, even if we take an air conditioner again as an example, when you set a particular temperature at a particular, say, 26 degrees Celsius, it can use its sensors to sense the temperature in the room, and then adjust the temperature in the room accordingly, cool down the room accordingly, and bring down the temperature to a fairly accurate point. That is again another advantage. They can perform things in a much accurate manner, because we are measuring things digitally. We can make calculations much more accurately, and then we can produce outcomes much more accurately. And one of the other main advantages is flexibility. So for example, many systems that we can do them or develop them as digital systems we can also develop them as mechanical systems. For example, if we are building a robotic arm that is moving some objects from one place to another, we can develop it as a digital system using some sensors to sense the item and then move it accordingly using certain stepper motors and then leaving the item on the other place and few other parts. We can also build the same thing as a purely mechanical system, a purely analog system, where all the control aspects are done in an analog manner. So we may have to build certain gearing systems and all these things to measure the movement, rotations, and so on. It is possible, but the disadvantage is if we want to make some changes, if we want to make some adjustments to the system, we have to do a lot of adjustments in the actual hardware itself, and it may be very difficult. It may sometimes be taking a lot of time. Whereas if it is a digital system, we only need to change a piece of code and maybe recompile and upload the code to the system, and then the new instructions can be executed by the system, because as long as the system is capable of it, we can change the instructions and give it new instructions. Whereas if it's an analog system, we sometimes have to make more significant changes to the underlying system to make it do something different. So that flexibility aspect is an important differentiation that we will find with digital systems. Then cost is also an important factor, particularly when we think about large scale implementations. So if we are only making a single unit, that is one thing. But if we are replicating across a large number of units, sometimes if we can make them as digital systems, replication and the amount of components needed and so on will have a lot of cost advantages when we are building them as digital systems. So for example, instead of things that are designed with many motors and things and all these things, we can bring in all those logic into a program, and we can implement the program logic and then only control a few different components, and the overall cost can be brought down significantly. And also one of the main advantages, particularly from a cost point of view as well, is what we can identify as implementation errors. So for example, if we are making a system as an analog system, we'll have to build that system and then we have to trial it, and if there are any issues, then we may have to go and fix it, and we'll have to go in that route. But if we are doing them as digital systems, the advantage is all the logic is as part of a program code. So then we can do verification of the codes, and even when we are implementing, we can go and fix these errors much more effectively, so that we can reduce the amount of errors, and also even if there are any errors present, we can fix them much more quickly, much more efficiently with digital systems. So this is particularly comparing to analog systems. It doesn't mean that analog systems are not at all useful. There are certain applications where analog systems are perfectly fine, and we will still keep on using them. For example, the controller for a fan, we are still using, in most cases, analog controllers. There are no digital controllers in most fans, even though it is possible to use them, because it is enough in that situation. But if we want, we can have digital controls. But in some cases, having digital controls will be much more advantageous because we can do more with them. So in that case, we will build more digital controls, more systems with digital control as we move forward. Then another concept that we will revisit quite a lot during this course is what is called signals. So when we talk about digital control systems, we take that the control logic is implemented in a digital device, but then also all the communication, all the information passing will also happen in a digital manner. In generally, what we classify as signals is anything that we can measure that changes with time. Say, for example, uh, it is something that has to be a variable, not a constant value. It's something a variable value, and it will change over time. For example, if we take the temperature of a room, that can change over a period of time, so that can be a signal. If we measure the temperature of a room, that would become a signal. If we measure the voltage across something, and if it will change over time, again, that can be a signal. If we are speaking and we are producing some information and that is changing over time, again, that can be considered a signal. So that is the basic definition of a signal. And signals can be either simple signals or complex signals. So when we say simple signals, so for example, if we plot in a graph saying what is the temperature in the room, so then we will measure the temperature in the room and we will plot it in a graph, and that is a signal that we can measure over a period of time, something that changes over a period of time. But when we take speaking, a person speaking, that is also a signal. But when we say, for example, record that speech, that will be a fairly complex signal because it is going to carry a lot of properties in that signal. It will be various frequencies, various amplitudes of sounds, so that will be a much more complex signal. So sound signals, thermal signals, so there can be a number of examples. We will cover signals in a much more detailed manner in one of the upcoming lectures, but signals are also an important part of digital control system. So when we think about signals, we can categorize them into number of categories. Say, for example, binary signals. So these are things that are say like zeros and ones. So for example, if we are monitoring something, an existence of something, say if a door is closed, if we are monitoring if a door is closed, then the whatever the sensing part that is coming from that thing will be recorded as a binary signal. Say, for example, if the door is closed, we will have a 1. If it is open, we will have a 0. So likewise, we may have at different points, we will get different signal. Then another category or another way we can categorize signals can be based on digital signals or continuous signals. So between digital and continuous signals, the main differentiation is digital signals are going to be represented as finite amount of information. So they are represented as finite amount of information as a signal. Say, for example, once we record a sound and store it in a computer, we would store it as a digital signal. Whereas the actual sound that is being produced and maybe that may be carried over through a microphone may be a continuous signal, will be a continuous signal at that point. But when it is get recorded into a computer, it will be converted into a digital signal. So we will talk about this analog and digital conversion also later on in this course. And other than this, we will also have few other categories of signals such as fuzzy signals or stochastic signals. These are again something that we will not be focusing on in this course, but these are either not well defined signals or unpredictable signals, but that is not something that we are going to be focusing on in this course. We will be mainly focusing on with digital and continuous signals and the conversions between those two. So then when we think about systems and signals, there are a number of places where we will use signals. Signals can be given as inputs, and sometimes we will get outputs from systems that can also be sometimes considered signals or values that can be measured. So, for example, if we take a system uh, and if the system is being given some input, so from external entities we are getting some inputs, and that is input signals, also they can receive those signals as input. Then they may also receive additional inputs in two categories. So one is expected inputs that we are providing to the system. Then we may also receive what is called disturbances. So these are things that are impacting the system but not given by the users. For example, again we will go back to the example of an air conditioner, and you setting a particular temperature on the air conditioner is a input, that is a manipulated input. You are giving that input by purpose. It is a purposeful input. But whereas if the temperature outside changes, if it is raining or if it is becoming more hot during the day, that is not a manipulated input, that is a disturbance, because it is impacting upon the system. Because if the outside gets hot, the room will get hot, so the air condition will have to function differently. But that input, that information is not something that is given by the user. So we will consider that as disturbances. So with that, disturbances are something that we are not able to control, because if it is an outside temperature, if the sun is hot during the day, that is not something we can control. But whereas we can control input signals, the manipulated input signals, because we can change the temperature as we want. Then when we think about outputs, the outputs that are being produced by the system, again we can categorize them as two. One is external outputs and internal output. So external outputs are produced as an outcome of the system, and we may have some sensors to check that. Again, if we take the air conditioner, it is producing cool air and feeding it into the room. So we may have a sensor in the room and sense the temperature that way. Whereas certain other systems may produce some internal variables, internal process variables, and those things may be internal and may not be measured externally. So these are some of the different variables that we may come across when we are talking about these type of systems. Again, we will discuss about this in much more detail in the coming weeks, when we are particularly focusing on control systems architectures and how different things can be interconnected, sensors and actuators and so on. So all these things we will be covering in much more detail in the coming weeks. Today we are only going through this as an introductory lesson. Then when we think about other things that we will be covering in this course, we will also be discussing about other systems that are related to control systems or related to signal processing. So things like signal generators, signal processors, sensors, and receivers and transmitters. So we will cover some of these other systems as well, not just the control systems. So we will be main focus of the course is about control systems, but because control systems are controlled and measured using signals, we will also significantly focus on signals and these related systems that are going to be auxiliary to these control systems or feeding into these control systems. So we will focus on these type of systems as well. So for example, we may use a sine wave generator to produce an input or produce a particular type of input into a system, give an input to a system. We may use certain type of signal processing like filters, samplers to to convert them, maybe to convert them from analog to digital and so on. We may use certain type of sensors to convert from, say, physical phenomenon and convert them into signals. Say, for example, we may use a microphone to convert something into a audio signal. Um, we may use transmitters and receivers to send and receive signals over a length of uh, distance. Say, for example, say we may transmit a signal and receive it at another end, and we may build systems that function using that type of communication. So we may focus on these other type of systems also during this course. So generally, when we talk about signals, there are a few ways systems can be represented. So one of the simpler ways they can be represented is using, say, for example, using a graph or a table. So we may plot it as points in a graph, or we may take these points and mark them in a table. So we may take these coordinates and have it as a set of data points in a table. Or sometimes what we may also do is represent them in the form of a function. So certain signals may be represented as a mathematical function. So that may also be possible. So depending on the situation, depending on the circumstances, we may do both. And another thing that we would come across when we are using signals, particularly when signals are being transmitted over a period of time, period of length, or across different mediums, what we may have is a mix of information and noise as part of a signal. Say, for example, what we may intend to send is a piece of information, but due to, for example, like magnetic interference and so on, there may be additional noises added to that signal. Then we may have to split or separate that noise and the actual information to use in our systems. So again, this is where we may use certain type of filters and so on to get a better outcome from the received signals, so to separate the noise from information. Then when we discuss about control systems, we will discuss about a number of control system structures. We will particularly discuss about open loop and closed loop control system structures in this course, but there are many other structures as well. We will briefly touch upon them, but we will mainly be focusing on open loop and closed loop systems. So again, we can understand this with an example of a fan and an air conditioner. In the case of a fan, what we do is we set a goal. We set it to run at a particular speed. It will rotate at a particular speed and it will keep on running. So there are no additional information is provided. There are no measurements taken. It will keep at it according to the goal that is given. So that is an open loop system. Whereas when we consider an air conditioner, that is something that we would categorize as a closed loop system, because there we would set a goal, we would set a temperature saying the room should be at 26 degrees Celsius. So that is the goal that we are setting for the air conditioner. Then the controller, the system, will make measurements of temperature inside the room, and it will change its behavior. It will change the compressor, how the compressor is functioning, fans are functioning, and all those things. It will change the behavior of the system to achieve the set goal. If things change, again they will change. If the room gets warmer, it will cool more. If the room gets cooler, it will cool less. So likewise, it is going to measure and change its behavior. So that is the closed loop system. So we give an input, something changes, and then that is again informing the input. So it is like a closed loop. So if it is a open loop system, what we have there is, say, we will start with an input, we will set a instruction, it will function as it is. Whereas in a closed loop system, we will set an instruction, then it will do some measurements there, and that measurement will again inform back to the system. So that is the main difference between closed loop and open loop control systems. So these are the two that we will be focusing more in this course. But in addition to this, there are other structures for control systems as well. These we may not focus much in the course, but you may sometimes come to some of these when you are doing a project as part of the course. So things like supervisory systems, cascade systems, feed forward systems. This is something similar to feedback systems, but fairly different as well, and so on. So we may come to discussing some of these as part of this course later on, but our main focus will be on open loop and closed loop systems. So if we look at closed loop system with the example of an air conditioner, so the reference point is what we set as the temperature that we want. So we say 26 is the temperature that we want. That is the reference that we set as an input from the user. So the user is setting the reference point there. Then the controller will take that reference point and it will create what is called the system inputs about how fast the fan should rotate, how much the compressor should function, all those things. The controller will produce the input for the system itself. So the actual system will be controlled by the controller. Then the system will produce the output. So that is the changing of temperature in the room and so on will be produced by the system. Then whatever the outcome that is being produced by the system will be again measured by a sensor. So what we will have is, we will have a sensor that will measure and it will produce a measured output. So that will be again a temperature. For example, it may produce an output as 26. So then when it is compared, it is achieved, the reference is achieved. But alternatively, if it is measuring the temperature as say 28 degrees, so then it will produce a difference here and it will produce a measured difference here. So that measured difference or the measured error will be used as an input to the controller to fix that error. So if the room is not cool enough, if the room is still 28, it will cool more. But when it is achieved 26, it will not try to cool anymore. So that is the main point about closed loop systems. So this course is mainly going to be about how we are building digital control systems, particularly closed loop control systems, and how we are using various digital components to build that. So that is what we will focus in this course. And as a practice, what would be expected from you is to participate actively in particularly the project and all the related activities. What sometimes may happen is one or two members of a group may try to work on the project and others may not contribute as much. But main disadvantage with that is, unless you are actively involving with this, you may not get the same level of understanding of these things. Because knowing these things, for example, whatever the things that we learn as part of this course, even though this is about digital control systems, we are mainly learning about the technology aspect of it. We are learning about electronics, we are learning about embedded systems, microcontrollers. So all of these things will be part of our course. So those the knowledge that you gain from those aspects will be useful in many other courses as well. When we are studying networking, Internet of Things, embedded systems, or for various things, many things that we cover as part of this course will be useful. So that is one of the reasons. Even things like multimedia, audio productions, video, and all these things. So students going into any sort of specializations will be benefited by having a good understanding of this course, even though we are studying it from a digital control systems perspective. So try to take it from that understanding and try to engage with the course as much as possible. And as I said, we will you do a group project as the main assessment component of this course. It will be a group of 4 to 5 people, and you will need people with different sets of skills as part of this group project. So things like electronics, programming, even things like research and project management will be something required as well. So, and also as part of your overall curriculum of the degree program, this is one of the significant projects that you will do. In addition to your final year research project, this is also one of the main projects that you will be doing as part of your degree, and it will be very much valuable when you can do a good project in the case of participating in external exhibitions, for example, competitions, and also mainly in terms of a career perspective. When you're going for internship interviews and so on, there will be a very big value when you participate and do these projects in a good level. So again, we will discuss about this project in much more detail in the coming weeks, and we will start the actual work preferably once we start on-campus classes. But actually the planning of the project grouping and so on, we can start maybe by next week. So that's all I have to cover for today. As an introductory part, we only covered a brief introduction to this course. And as always, one of the main things that you need to do is always, if you have any issues with the course, if you have any doubts, questions, problems, it's always good to ask early and ask often. So you can contact me, you can ask those questions during the lecture time, or later on you can contact me through email or messaging or anything, and we can do that as well. So before concluding, are there any questions? If there are no questions, we may conclude for the day, and see you next week at the usual time of Mondays. Until next time, thank you for joining, and bye.